Institute for Computational Engineering and Science in Austin. And he's generally interested in meta-analysis, model order reduction, uncertainty quantification, inverse problems. And today he's going to talk about a topic that fits very well with the workshop. It's reduction strategy for large-scale data-driven PD-constrained Bayesian inverse problems. So the stage is yours. You've got 45 minutes, and I'm going to sit down now.
Thank you so much for the introduction. By thanking the organizers for inviting me. Unfortunately, I couldn't do it because of the visa issue. You know, some of you may know that I'm a Vietnamese, and one of the interesting aspects of the Vietnamese citizen is that I need a visa to enter every country, almost everywhere. So, but for this time, I don't know, 2 weeks ahead of time, but it doesn't seem to be enough for the UK embassy to process my visa. So I'm really sorry about that. I couldn't come. Posterior, if not, let me just quickly talk about that. So on the slide, on the box there, as you can see, Y observed is the observation data. G of Q is the so-called forward map that takes the parameters in the equation below that you see at the subjective. So for simplicity of the presentation, I look at the elliptic equations. Which is the log thermal conductivities, and W is the solution of the forward equations, right, which is the states as well. So we tried the data misfit is an effort to try to match, to look for the parameters U to match the observations. But you know, typically inverse is what two poles, so you need some equalizations, and the second term you can usually consider realizations, or you can be actually negative of the log, the prior if you put Bayesian was before. Okay, so let me talk about a few challenges with this in the problems. First, there's three key players. The first player is the observation. If the observation is large, which is applicable for many of my applications, especially climate inversion or earthquake inversions, where we have measurement data gigabyte, petabytes, and seconds. So that's become problems if we have to deal with this such a big amount of data in the inverse problem. The second obstacle is the state W, right? As many of you there, but we need to discretize EE, and depends on the mesh size, the dimension of W could be very large. And if the dimension of the W is large, and if the problem is not linear or even linear, it's very expensive to solve each of the PD or PDEs, right? Especially when we talk about Bayesian problem with MCMC, right? So each MCMC step requires a solution of the forward equations, and if the equations is expensive to solve, that's going to be problematic. And the third obstacles is high-dimensional parameter space, U, right? Again, which also deep in some function space, typically, and you have to discretize U, and as soon as you discretize, you have a mesh, and depends on the mesh, you can have very high-dimensional parameter space. And if you work with MCMC before, you know, those we have to deal with the curve of dimensionalities. In particular, the higher dimension the U is, the more or exponentially many more MCMC steps that we need to take. That means increasing exponentially increasing the number of the solve, which is very impractical. Okay, so in this talk I'm gonna show you some of our effort in my group at tackling these F's on these objects. So let me start with a method that we call randomized misfit approach, in which we try to deal with the dimensionality of the observation. So the question that we want to ask is, can we work with some low-dimensional subspace data? And we also want to use a lot of resources after we use the number of data. Yet, we don't obtain reasonable solution. This is how to be too invasive. But I think we can show you in a second it's possible if we take some particular approach. And the approach that we're going to talk now is the so-called randomization. Blue box, as you can see, the misfit is the first terms. The L2 norm here, we assume that the Gaussian errors with the gamma as the covariance. On the right hand, the second term is still the regularizations. Okay, so notice that we introduce R, which is the random vectors whose mean is 0 and covariance is actually identity. So any random vectors that have that property is okay. So the only constraint is that the dimension of that random vector is the same dimension of the data, which is capital N. Okay, so we're going to do in the second equation, right, what we're going to do is we rewrite the first term, which is the misfit term, by inserting the random vector R. And this is a simple algebra. I don't have time or the means to discuss here, but it's very simple, trust me. So we can basically randomize the misfit term into the first term and the second equations, and we turn a deterministic problem into the stochastic problem with expectation with respect to R. So they are completely equivalent up to this point. Okay, so the next step that we're going to do is something very actually silly in a sense, because we're going to discretize the expectation using Monte-Carlo technique with little n number of samples. Okay, so each sample requires to sample R from its distribution. So Rj is random vectors from the distribution whose mean is 0 and covariance is identity. Okay, so we have a little n of random vectors R. So in the last equation, we simply combine on the random vectors, put each of them in a column of a matrix. We call it sigma, the pink sigma that you see over there. Okay, and then we can rewrite the Monte Carlo approximation of the cost function J as the green box, which we call Jn tutor with n samples from the distribution of R. And if you look at the blue box and the green box, the only difference is the sigma transpose matrix, right? And that's actually crucial, because sigma have the dimension of capital N, little n, right? So have capital N rows, the same number of the data dimension, and n columns, little n, right? The number of random vectors. So if you take the transpose, then you notice that the misfit is now has much lower dimension n, right? Especially if little n is much smaller than capital N, then we substantially reduce the data, right? So this is a projection of data into a random matrix or random space. Of course, at this point you may ask, okay, all these things, Monte Carlo is very inaccurate, and doing this is actually make things worse, right? But it turns out that it works, and also, why, whether n could be much less than capital N, right? And we know that MCMC require a lot of little n in order for it to converge. But it turns out that it works, right? Even very little n, order 1 n still works. I'm going to show you now. So why this method works, right? So this method works well because of two main ingredients. The first ingredient is a so-called Johnson-Linda-Strauss lemma. So this lemma says the following: if you have VIs are all of your n-dimensional vectors, or n assumed to be big, and this theorem says that there exists a map P that take capital N dimensional data into little n dimensional data. such that it still preserves geometries, right? So in Hilbert's space, you know that as soon as you preserve geometry, that only matters. And you see that the figure that I showed there on points in high-dimensional space through P, you can get to a low-dimensional space on E. And the error that you make is epsilon, and epsilon can be determined as a function of n. And in fact, it's actually 1 over square root of n. And one more important point is that this error is independent of the dimension of the original data, in particular n, right? So the error that you make in these projections, which is epsilon, is independent of the original data, which is really important, right? Because that's what we want to do. And again, you know, if you try to relate it to Monte Carlo techniques, and you know, that's also the number of samples actually independent of the dimension. So that's kind of, you know, relationship. In fact, we can show that we can derive the Johnson-Minor-Strauss theorem from MCMC and show why the number of random dimension is proportionally to 1 over square of the error. Okay, so that's the first ingredient. You make a little bit error in projections, but it's okay, right? We make independence is the dimensions. Okay, so the second ingredient is the Morozov discrepancy principle. So if you look at the misfit term that I put in the blue box, the Morozov principle says that you don't have to solve your inverse solution, which is U star, all the way to match the observations, right? Because you know the observation have the errors or random noise. If you try to match the observation, you will match the noise, and you will guess bad solutions, right? That is well known in the inverse community. So Morozov said that, okay, you just try to match the observations. As soon as you reach the one level, then you should stop. And that's what we call Morozov discrepancy principle solutions. And this is exactly the pink box that I showed you here. Okay, so combine these two ingredients. Notice, recall, right, that I make a little error or big error. It doesn't matter, right, in the projections, but in the projection of the misfit. But on the other hand, the errors, as soon as it is the same as the noise level, we are okay, right? By triangle inequality, we know that, you know, solution for the reduced data should be good. In fact, we actually can show a theorem that we call statistical Morozov discrepancy principle. This theorem just says what I just said. It says that when you project the data into a random space with dimension independent of the original dimension of the data, but if you assume that your reduced solutions, when I say reduced solution, I mean the solution or the deterministic solution of the problem with reduced data, as soon as the reduced solution satisfy the Morozov discrepancy principle, right? In particular, the reduced solution match the error within the noise level, then it is also a Morozov discrepancy principle of the original function, cost function, okay? So you see that the first equation is J theta M, and the first equation say that, okay, if we assume that our reduced solution satisfies Morozov, and the second equation that says that the U theta, which is reduced solution, also satisfies the Morozov discrepancy principle of the original cost function or the original problem. And this is actually important, right? Because what we want is that our solution is also some kind of approximation of the original solution. And we show that is, you know, again, this is a statistical approach. So this result is satisfied or it holds with high probability, right? In particular, it's exponentially large probabilities. Okay. And in fact, for a linear problem, we can do a little bit further. We can show which, you know, not expected, right? The optimal cost functions of the reduced problem is actually epsilon away from the optimal cost function of the full problem, which is J star, right? And we also can show that the reduced solution and the original solution actually, we can bound them, right, in terms of the error, projection error that we make. Okay. And let me come back to here for 1 second. In this theorem, we can also show that, in fact, the epsilon can be order 1, and we still can get the Morozov discrepancy principle solutions. And that's explain why the method is successful. In particular, what we have tried so far, let me summarize what we have shown. We actually combine stochastic programming and random rejection theories to provide a more complete theories. Notice that the random rejection thing that I just mentioned to you, right, or the stochastic approach that I just mentioned to you, actually been known for a few years or decades. But people try it out and don't understand why it works even for a small number of random vectors, right? It just works, and it's just amazing. As what we show here is actually we are explaining the results in the statistical Morozov discrepancy principle show that yes, it is it works because of that combination of the random rejection and the Morozov discrepancy principle that allow us to use only very small number of random vectors, and yet it still works. And the key again, Johnson, Linden, Strauss, and Morozov. Okay, so let me show you. The thing that I haven't mentioned to you is the random vector, right? It turns out that, remember that as soon as the random vectors whose mean is 0 and the covariance identity, then the method will work, right? And it turns out that there are many sparse random distributions, right? What I show you in 3 figures here on the left is 10% random vectors, which result in a 10% random sparse matrix sigma. And the middle one is 20%, and the last one is 50% sparse. So the beauty of this thing is that when you do projection, you don't need to combine all the data, right? Especially the projections is in the product. If you're thinking about a large data, you don't want to access all of them. And this is, even though it's an offline process, we want to make it efficient, right? And especially random matrix time, a full vector can be done efficiently, and that's why we like it. And let me show you some numerical results. Here we look at thermofilm problems. Again, it's just for simplicity. On the right-hand side is the exact thermal conductivity with the full problems with 1,333 data points, capital N. And we want to invert for that blob in the U, which is the log thermal conductivities. On the left-hand side, we show the result, the reduced inverse problem results with 31 random projections with 67% sparse random matrix. And you see that is actually not very good, even though you see a little bit of thing in the middle, right? Let us increase a little bit, 51. So now we use 51 random vectors. You can already see that the blob actually show up in the middle, right, compared to the right, which is the exact one. And if you want to make it 100, then you can see that we almost recover the solution on the right-hand side, right, on the right-hand side, with all the magnitudes of smaller data. Okay, so let me also show you a result for 3D. And the right-hand side again is the full problem with 2,474 data points. Basically, that's the final element nodes. And on the left-hand side with 50 random rejection, right? Again, 67% sparsity. And we actually will see something like 3, blob inside the box already. But if you make it 100, we almost recover the 3 blobs on the right-hand side. Of course, the shape is a little bit different, but if you do oil recovery or geophysical exploration, this is actually what matters, right? To know where the oil reservoir is. Okay, so I have shown you how the method works with the theories, but let me show you some reductions, right? Remember that we want not only to deal with the reduced data, which is supposedly cheaper in terms of I/O, right, input and output, but also we want the cost of solving the inverse problem with reduced data reduced. And let's try to see whether that is true. So in this table, I show you a 2D elliptic inverse problems. We solve the inverse problem or deterministic inverse problem using trust region in exact Newton CG. So the detail is not important here, but you look at this table, right? The first line is the deterministic approach with full data. And on the last column is the number of PD solves, right? So for us, in terms of inverse problem, Bayesian inverse problem, our currency is the number of PD solves, because the forward equation is supposed to be the most expensive part, right? Because you don't want to solve that a lot. So if you do the deterministic way with full data, you need about 2,423 PD solves, right? And on the lines below the deterministic line are different type of random vectors, right? R, remember, and all of these satisfy the fact that the mean is 0 and the covariance identity. So random marker is the -1 and 1, right? Some of you may know about that. At the optist is a 67% sparsity that I just showed you. And I also show you about 95% sparse, and even 99% sparse, right? And the last two lines is the standard Gaussians R and uniform random vectors. And as you notice that on the last columns, especially the pink one or the other numbers compared to the orange one, if we use random projections, we actually can get about half the PD solves, right? Not only we get the good or reasonable loss of discrepancy satisfies in the solution, but also we reduce the number of PD solved for all these randoms, right? And of course, we are interested in the sparsity. Okay. The 3D is a similar story, but we get less number of PD solved, because for the deterministic one, full data is just so good to take a 331 already, right, to get 331 PD solved to get the solution. We still less, right? For example, we most of like 280 or something below, but not much improvement because of the original one is only taking less number of PD solves. Okay, but the point is that we actually less, right? But not more. Okay, so up to this point, I have shown you one way that we pursue to reduce the dimension of the data, and also the number of PD solves, right? What I'm going to show you next is the thing that we have been doing, and I think is exciting to some of you. In particular, what we care about is now how we do the state and parameter reduction. Remember that we have three key players: the data, the state, and the parameters. And the approach we take here is inspired by the domain decomposition methods. So what I'm going to show you is the conductivity on the left of the figures, the conductivities. In the right figures, we purposely put the observation, right, to measure the Y observed or the data, the thermals or the temperatures at the points at the lower part of the thermal fin. On the right-hand side, we solve the inverse problem, right, using all of these data, of course, and on the full domain. As you notice, right, we only can recover the lower lobe quite well, right? But the top one, we almost don't see anything. In particular, you don't hope, right, that we can have a lot of reliable reconstruction of the second lobe or the rest of the domain if the domain is far away from the measurements, right? So this is intuitively what we should think as well, and it's shown here. We can only recover things that are close to the measurement points. So, so the question is that, if only regions close to the observation are well informed with the data, why should we invert for the regions that are far away, right, where the results are uncertainty or has a lot of errors, right? For example, in this case, we have a huge uncertainty of the errors in the upper half of the thermal fin. So, using that observation, we're going to do a truncation domain inverse problem approach. So let me tell you what it means here. So by just showing the idea behind it. So on the left columns, on the top figure is the outer domain, right? And the left side of the domain, which is the blue bar that you see on the slide, is where we put the observations. Okay, and again, it's an elliptic problem that we deal with, and we want to invert for U, which is the log conductivities. Okay, so the idea is the following. So as we can expect, right, the omega d, we divide the domain into two parts. Omega I, where we do the inversions, omega d, where we truncate, right? Because we know, I'm going to tell you where you truncate later, but assume that we know where to truncate right now. So I know, or we know the truncated domain omega d, so we're going to remove that part, right? So we still have an elliptic equation, or the PDEs, in the blue part, or the omega I, right? But of course, we need, some of you immediately ask me a question right there, right? How do you deal with the battery where you truncate the domain, right? So let me tell you in 1 second, right? We're going to use the Dirichlet to Neumann map, right? Basically the flux. We're going to try to replace the home domain omega d, the part that we truncate, with a flux. Okay. So what we do next is the following. We're going to have three equations, right? Three equations. On the top left is, again, the equations in the discarded domain, or the truncated domain, omega d, right? And you notice that we have the Dirichlet battery condition on the gamma, which is the battery separating between the inverse domain and the truncated domain. This is the standard technique in the domain decomposition approach, on particular Dirichlet to Neumann approach. On the bottom box is the PDEs in the inverse domain, right, which is omega I right there. Okay, and the communication between the truncated domain D and inverse domain I is through the Dirichlet to Neumann map lambda, right? If you look at the last equation on the box on the bottom right, so it connects to the domain that you truncated with this Dirichlet to Neumann map, and the Dirichlet to Neumann map is given by the box on the first column, right, the bottom one. So it's defined as lambda phi is equal to exponential mu d gradient of w, and this is the standard Dirichlet to Neumann. And notice that the key thing is that the Dirichlet to Neumann map is a function of the solutions, right? Not only the solution, but the parameters in the truncated domain, right? So we run into a dilemma here, right? We want to truncate, but we see that the exact Dirichlet to Neumann, where we can completely replace the truncated domain, is a function of the solution in the truncated domain and also the parameters, right? So, so how do we deal with this? There's many ways to do it, but let me just explain to you one way to do it, right? Which I'm going to cover that again in a few seconds when we compare with the other methods. Because this is the reductions workshop, you can see, right? Something that you don't know, especially lambda, if you don't know, right? You try to hope it, okay, can we actually replace this lambda by some reduced sum model, right? Or for this problem, this is a linear, right, with respect to phi. In fact, I mean, it's actually not really linear because it's complicated, so in general. But this one is okay. But what we're going to do is that we're going to, one way to do it, which not our approach, right, by Salvo and Daniel Cavetti, what they did was to sample, right? You sample UD, right, the first box on the left-hand side, you sample the whole thing, UD in the truncated domain and the inverse domain, right? You throw a few samples on the parameters, and for each sample, you solve the solution or the equation, the forward equation on the whole domains, okay? And then once you have the solution of the whole domain and you have the parameters, then you can construct the lambda or the Dirichlet to Neumann map at that particular parameters. So you do many of them, and so you have you can imagine that you have if I put each of the solution or each of the Dirichlet to Neumann map associated with each random samples of the parameters in one column of the matrix, so then you have as many columns as the number of samples that you use, right? So you solve upfront the full domains, whole problems at the number of field, or number depends, right, on the full domains, and you construct the snapshot or the instances of the Dirichlet Neumann map at these parameters. Okay, and then, you know, I'm a purely proper orthogonal decomposition guy, so I just looking at the snapshot, what I'm going to do is do SVD, or the proper orthogonal decomposition, to get the important subspace of lambda, or the subspace which hopefully describes or reflect what lambda lives in for any parameters, right? So once you have the linear lambdas, when you have lambda can be expressed as the linear combinations of the basic vectors, or the POD basic vectors, right? What left or unknown is the coefficient in front of basis vectors, right? So the good thing at this point is that now I can completely ignore the truncated domain, which is the gray regions, right? Because I know the Dirichlet to Neumann map, right, approximately up to the coefficients, unknown coefficients, right? So the idea is that instead of inverting for UI, right, the green one in the box, the bottom box on the right columns alone, which of course you can't do it, right, because you still don't know the Dirichlet Neumanns, right, because we still don't know coefficients. The natural idea is to invert for UI, which is the coefficients, right, or the thermal conductivity and the coefficient of the PODs in the Dirichlet Neumann map at the same time, right? So we do simultaneously inverting for the coefficients of the PODs and the parameters in the domain. So at this point, you see that we can completely remove the domains, right? The omega d, the gray regions. But of course, you have to solve a little bit bigger than the problem than we would like to be. But the beauty here is that you replace the whole gray region with one dimensional less. In this case, from 2D domain into 1D domain with a few coefficients, right? So that should pay off, and we will show you later. So what is the significance of doing this, right? Truncate or throwing away the domain that is actually uninformed by the data. So in fact, we do two things at the same time, essentially. So first, by truncate the domains, right? Each inverse solution. Notice that, right? I'm talking about Bayesian inverse solution right now in this context, right? Because what you really care about is the deterministic inversions, then this method will not work. It will not work well, right? In particular, it will not pay us out. Because you can just simply solve the original deterministic problem once, and that's good, right? Versus this method, you require a number of deterministic inverse problem, or the forward equations, many times as many number of samples of the conductivities. But if you think about the Bayesian inverse problem, where you have to solve the forward again and again, right, then this becomes beneficial. In particular, each forward equations is now smaller because we are in the omega I, which is smaller, the domain, right? So you actually reduce the number of states immediately by throwing away the domain that is actually not well informed by the data. And the second, which is important observation, is that when you throw away the uninformed domain, you automatically throw away the parameters associated or residing on that domain as well, right? So you are automatically cutting the number of states and the number of parameters at the same time, and that's what we call the double model reduction technique. But it's nothing more than domain decompositions, right? With a tweak in applications, right? Especially in the inverse problems. Okay, so bear with me. By doing that, we can cut down the state and cut out the number of parameters. Then we can move to some of the examples. by the way, actually, theoretically, we still work on this method and try to show some of the theoretical results. We haven't got any yet, except, for elliptic problems, you can completely replace the truncated domain with the dirichlet one, right? Yet, you still can get the correct solution, right? And what I mean is that the correct solution in the domain that are left, right? In particular, the solution in the domain that we are left using this technique with exact dirichlet one is nothing more than a restriction of the solution of the original domain, right? On the smaller one. But that is well known in domain conversational elliptic theory, so that's not something new. Okay, so I'm going to show you some numerical results here. Again, 3D or 2D inversions. On the left-hand side is actually a picture of the cat. My student loves cats so much that she wants to invert for a cat. And in this case, this is a oh my god cat, right? Where the cat actually opened her mouth, saying something which, of course, we don't understand. On the right-hand side, actually, before going to the right-hand side, you notice that on the pink dot, hopefully you can see over there, right, surrounding the head of the cat to the cheek of the cat on both sides. So these are where we have observations. Okay. Now on the right-hand side, we do the inversions with the full domain, right? What we got is, as expected, right? We can recover things pretty good, right? On the around or surround or close to the observation, in particular, surrounding the upper half of the battery, right? Close to the cheek and close to the top of the cat. But other than that, it looks very bad, especially on the bottom part of the domain, right? You cannot recover anything, especially the mouth of the cat. Okay, so let's look at the this full domain solution one more time. Again, up to this point still deterministic, and we'll start talking about statistical in 1 second. Okay, the left figure, there are 3 figures here. The left figure is, again, we just saw the deterministic solution on the map, if you wish, of the Bayesian inverse problem, right? The maximum a posteriori point. This, which is nothing more than solution of the deterministic inverse problems on the which is on the left. We can recover pretty okay or good on the left part, close to on the upper part, right, close to the battery where we had the measurements. Okay, so what I'm going to try to say next is to tell you what we actually or what kind of methods or techniques that we use to determine where we truncate the domain, right? So if some of you may be familiar with what I worked before. So one way to do it is to solve deterministic optimization to get to the map points or to the highest mode of the Bayesian's posterior, right? And then you estimate the uncertainty or the covariance of the posterior there. In particular, we can show, of course, linear only, right? But for nonlinear, we can approximate the covariance of the posteriors, right, using the inverse of the Hessian at the deterministic solutions, right? So what I show you is in the middle is the point-wise approximate posterior variance at all the mesh points, right? And you may say, oh, computing the Hessian is expensive. Yes, it is, but we have a Lorentz approximation approach, again, using randomized technique, in particular randomized SVD, to approximate the Hessian and its inverse in scalable manners, independent of the dimension of the PDs and the parameters, right? It only depends on the number of informed modes that is dictated by the data. So as soon as you accept with me on that we can compute the approximation of the covariance of the posterior efficiently, then here it is, right? As you can see, the yellow part are where the uncertainty is high, right? The rest are small. Of course, we still don't understand why the top 2 corners of the domain where we have the data, but yet we still have a high uncertainty. I don't know yet. Someone checked the bug in the code, but she didn't find a bug. So something else that we need to resolve, something, a typo or something somewhere. But the main point is that the yellow part is where the uncertainty is high, right? So if the uncertainty is high, right, then we should not deal with it. We should throw away this region. So in particular, on the right figure is the solution using the exact DTM map, right? We assume that in this case we construct the exact one, and that is what you get the inverse solutions, right? Of the problem on the truncated domain using exact DTM map that we're going to use as the reference solution later. So you see that is covered much better than the full domain, which is on the left-hand side. So the key important thing that I want to emphasize is that not only we reduce the domain size, the number of parameters, but we also get a better reconstruction. And this is actually intuitively correct, right? Because you have less number of parameters to invert for, right? So you should get better solutions in some sense, right? Just intuitively, right? The problem that we have the blurry figure because you have so much data, and we know that due to the ill-positness of that fact, then we don't hope that you can recover things well. But if you have less parameters, then you should recover things better. And this is exactly what you see here on the right figure. Okay. So in the last few minutes, I'm going to go through this tables and another slide, and we are done. These tables make a comparison in deterministic inversions, and we're going to show you a stochastic one in the next slide, for many methods. So the full is the solution of the inverse problem with the full domain, right? So notice that you need to pay attention to the third line. The third line is the number of PD solves, our currencies, right? So you have 14,235 PD solves in order to get to the solution of full problem, yet we don't get a very good one, right? Result, remember? Okay, so for the next, the third column, which we call SAMP, it is a sampling technique. Remember that I talked about that, right? You sample the conductivity over the whole domain, you solve the forward equations, compute the Dirichlet to Neumann map, right, at these sampling parameters, and then using POD to construct the reduced space for the Dirichlet to Neumann operators. Okay, and then you invert for the number of coefficients of the POD nodes and the parameter in the domain that you are interested, or the domain that is well informed by the data. Okay, that's the third columns. And you see we already reduced like almost about half of the number of PD solved, which is good. Okay, so for the next three columns, we do something special, which I haven't had time to talk. Let me discuss very quickly now, where we actually do a model constraint approach, a goal-oriented approach. So you don't randomly sample the parameters to get a snapshot of the Dirichlet to Neumann. We solve an optimization problem to find the worst-case scenario of the parameter where the error in the Dirichlet to Neumann is largest. And this is inspired by what I did in my PhD thesis. We don't randomly sample, but we actually sample in a systematic manner, in a greedy approach, right, to find hopefully the best possible snapshots and the best possible reduced basis for the Dirichlet to Neumann. Okay, so when we have these goal-oriented snapshots, we do exactly the same, right? We compute PODs and then we invert for the POD nodes and the parameter in the domain informed by the data simultaneously. Okay, the projection, which is the fourth column, is a way to use the POD, replace the domains, right? The omega D, the truncated domain by POD approach, and this is a domain decompositions. The middle part, the ALT is the alternately or alternation approach, where we solve an optimization for the parameters separately, given the assuming we have the coefficient of the PODs, and then we solve for the parameters in the well-informed domain, and then we use that parameters fixed. We keep that fixed, and when we solve for the POD coefficients, and we do in alternating manners until things converge. Okay, and on the last column, second last column is where we invert both the POD coefficient and the parameter simultaneously. And the last one is the Dirichlet normal true, right? So of course, if you have a true Dirichlet normal map, you use the least number, so like 3,000 and then 41 PDOs. But the other method is a little bit higher, but yet we have about more than half number. Actually, it's actually fourth, right? 1/4 of the number of PD solved compared to the full, right? If you see the full domains. And then yes, we got a reasonable errors if you look at the next few rows, but it's not important right now, right? Just trust me that we get a reasonable error in various norms. Okay, so that's helpful if you do deterministic, but of course it doesn't help at all if what you care is deterministic. What we really have on the method we have a high impact is on the Bayesian technique, right? Or the problem when you have to do with MCMC, when you have to solve the forward again and again. Okay, so we have 1, 2, 3, 4, 5 columns. The first column is the Bayesian MCMC with the full models, right? And you see the middle part is the mean of the solution after we're done with the MCMC sampling, which we have about 2 million samples, right? 2 million PD solves. So we deal with that. That's why we choose a very toy problem here where we can do, right? So and then the top line is the low, which is I'm going to take the -2 variance, right? And the bottom row is a +2 variance. So this is like the credibility envelope for the solution, right? So the second column is the sampling technique with the random snapshots, right? The rest are using the goal-oriented snapshots with alternating direction method, projection, and mood. And the last one involve both, right? Solving both the POD coefficients and the parameter simultaneously. And as you can see, right, you do better than the sampling, of course, right? Compared to the second column, the rest of the middle part, right, of this, the rest of the column, we do better because they're close to the Dirichlet, the exact Dirichlet to normal map, because that's what we expect, right? We actually have a goal-oriented approach or snapshots, and we also have the better variance, right? If you look at the top, which is the -2 sigma variance, right, and then the bottom +2. So that's the all that we can share with you on the domain decomposition approach, right? We reduce the number of parameters and the states, right? And yet we get less number of PD solves for deterministic, and more importantly for the statistical, where we really care about, right? In this case, MCMC 2 million require 2 million PD solves, right? If you do full one, it's a lot costly, but if you do on a truncated domain, it's actually cheaper, right? Also, we need less number of parameters, and therefore your MCMC can converge faster as well because the number of parameters is less. Okay. So what we have to look at is 3 challenges, right? Expensive high-dimensional parameters and states and observations, and we look at the data reduction using IMA, which is a randomized technique, and then we truncate the state and parameters using the truncated domain or domain decomposition inspires approach. And our ongoing work is to compare this approach with the active subspace in reducing the parameters and the POD for reducing the states, which I with some of my collaborators right now. Thank you so much for your attention. Thank you. I'm sorry for the inconvenience.
That's okay. So, questions from the audience? I don't see a raised hand. Well, I have one question for you, Tam.
Yes, please.
So, in the randomized misfit approach, how do you choose the the distribution of this of the vector R.
Yeah.
I had several examples, and I couldn't really see what was a good choice and what's the idea behind.
Yeah. Yeah. So that's good. Let me come back to this slide. As you can see, yeah, we actually try many of them. What we are interested in is sparsity, right? And what we actually love is the 67% sparsity. Actually turns out to be outperform the others in many cases in terms of the error. Which actually, I'm sorry, I didn't show the error here. I only showed you the number of PD reductions, and I didn't show the error here. So that's why we have the list in statistically an error compared to the other sparsity approach. Does that answer the question?
Yeah, could you say again, because I clearly hear that. What is the distribution?
The alley optics, the third row of the table, where 70% of your vectors is actually 0.
Picking up. Maybe it'd be better if people emailed him first.
Yes, okay, maybe that's a good suggestion. I mean, 10, I think we are losing you with the sound. We cannot really hear.
Hello?
Hello, can you hear me?
I can hear you. Can you hear me?
Yes, we can hear you. But yeah, we had been difficulties with the sound. So I think it's interesting what you're doing, and if people have questions, they will email you.
Yeah. Yeah, no, it's good. No, that's perfect. Again, thank you so much for being there and for inviting me and accommodating me to give a talk remotely like this. Thank you so much.